Hello, everybody. Welcome to Ellensburg, Washington, USA. I assume we're functional, but even before I check that, let me let you know that it's 11:49 a.m. Pacific time, and this guest lecture will begin in about 11 minutes from now. So if you're watching the replay, you can skip ahead 11 minutes. You don't have to sit through this first 10 minutes or so of chatting. But let me find us on the iPad, make sure that you can hear me, and then we'll test the audio with our guest. Oh, looks like we got some 5x5s. I'm happy to see that. That is for damn sure. Hi, Melissa and Phil and Oscar and Papagino. Let's do a few of where you're viewing from and just bask in the glory that this thing's actually working. Backcountry Gary, I think I just saw your name. We got Alberta Gary with us. Hi, Gary. Lapine, Oregon, New Hampshire, Richland, Washington, Australia. Scrolling too fast now, but Daddy can be in charge here. Ottawa, Canada. Goldendale, Washington. Hello, Charlie. Lake Chelan. Okay, looks like we're going. Netherlands, Brussels, Belgium, Nova Scotia. Hi, Michael. Excellent. Okay, well, I'll continue visiting with you, but I feel like I want to make sure that Nicole, our guest, who you see over my shoulder, is functional. So let's make sure you can hear her. Okay, so we got a blue light. Yep, press and hold. We've got right there. Okay, you stay right there for just a sec. So, Nicole, what time did you leave the house this morning?
About 8:30.
8:30 from Richland.
Correct.
Made it up here a couple hours?
Yeah, hour and 45 or so.
Which way did you go?
I went up through Mattawa and Vantage area.
Yeah,
yep.
Very cool. Okay, yes. Can I double check that you can hear Nicole? I would love to see Nicole 5x5 if you can hear her. Oh, it is Nicole. Hey, we're rolling.
Sweet. Excellent.
Rolling. Okay. I'm going to visit with them a few more minutes.
Sure.
I think you can either stand, like Ian just stood here like a soldier. I don't think you have to necessarily, because, again, I'm going to introduce you as well. So if you want to stay here, fine. If you want to wander just a little bit, totally fine too.
Sure. Sounds
but
good.
I think we're good, huh?
Yeah.
Okay.
And I should just leave this on for now.
I think
correct?
so.
Okay.
Just
perfect.
With the idea that whatever you say.
Yes. Got it.
Okay.
Thank you.
Thank you. Mm-hmm. Oh, this is great. I'm excited. Okay, a little bit more saying hi to you. That's a relief that the audio is good for both here. Robert's in Chula Vista, California. Nina, hello. We got 225 people. All right. Thank you for making time for us here today. Yeah, I think I'm introducing the speaker, and I have some notes in my pocket that were written by Hannah Shamblin, so I'll see if I can read her chicken scratch here. Newport, Oregon, hello. Hot mic, Nicole. Yeah, Nicole's on hot mic. She knows that. That's right. Yes, and in case you're new to us, this is a series of talks on Fridays. Seems like a lot of people have watched the first two. So I'm glad that there's interest there. So I'm with you here for the first few minutes just to make sure things are functional, but I will momentarily disappear behind you and sit and direct the show, basically. Hoping it works. This is still really new, so I don't know. Just letting you know, mentally, I'm just assuming that it's going to break. And Nicole will be here, and she'll give her talk, and it's just, oh, well, you just kind of go away. I mean, I upgraded to whatever, Ventura or something. So who knows if the new OS is going to work with this. But that's what I keep telling myself. Like, if this all just, it's still just you in the room.
Exactly.
I mean, that's exactly what it was going to be anyway.
Yep.
So
for sure.
There.
Yeah. Great.
Okay. So
no, I think it's so cool that you're doing it this way. This is awesome. Yeah.
It's new for sure. It's not typical, but
it's nice to be able to reach more people,
Exactly. Don't we need to have people see what we're doing more than just private country club,
Yeah, I totally agree. Yeah, for sure.
Good. There will be a talk next week on Friday as well at noon. I will post that. I don't know how you found this one. Actually, can I ask you that before I go away? How did you know to find this, to join us right here? Did you just show up because you got notified somehow by YouTube? Or did you get an email or a ding on your phone or something? Or are you a savvy veteran of these live programs and you knew how to find this an hour ago in the playlist? I'll read a couple of your notifications. Okay, what kind of notification? Can you be more specific, please? What kind of notification did you get? Seems like that's hit or miss with some of you. Like some say, I got notified 30 minutes late or whatever. I did give you a schedule. Yeah, so you remembered. Good. Some of you are savvy veterans. Phone dinged. Text. Oh, you got a text on the phone. Oh, wow. What did the text say? Nick Zentner has gone live or something? I'm asking because, of course, I don't get notified. So however you're doing it, you're finding us. Got a pop-up notification. Okay, good. Well, whatever you've done, thank you for being with us. Okay, I think let me give you a shot of the room here quick, and then we'll get started. Our lecture begins in 5 minutes. Thank you for joining us today. We'll get you off the big screen here, Nicole. That's a bit of reprieve for you. You don't have to be projected. Like this is some sort of show at the Meadowlands or something. We don't need you up there all the time. So what sounds good to you after this? A little Japanese food or kind of a salad or a sandwich or?
Gosh, any of those things sound good. I love Japanese food, though. Wasn't expecting that to be the first thing that you said.
Yeah.
So, yeah, I'm open. Whatever you think is good. I'm
good. Well, we'll invite whoever wants to kind of just
perfect.
tag along with us.
Awesome. That sounds great.
And then I'm really into Hannah's volcano living with volcano.
I would love to come to it. Yep.
Should we drop in and listen?
She told me what it was about, and I'm very interested.
Oh man.
Yeah.
It's the real thing.
Cool.
For sure. Okay.
Excuse me.
Yeah, get those coughs out.
I know.
I feel for you.
I know.
Hi. I'm feeling like I can talk now. I got things working here a little bit. I'm Nick.
Nice to meet you. Thank you for all these years.
It's my pleasure. Yeah, your name?
I'm Dana.
Dana, it's nice to meet you. Thanks for coming in today. This is Bryce, the rock licker. This is Dana. So you guys can't miss one of these now because you are like center.
We have to be at everyone now.
I felt bad that I had to leave early last week, but
Oh, I didn't even notice. I'll have to watch the replay. The time when you took off. Busted.
Hi, Nick.
How are you, Jeff?
Doing well.
yeah, 'cause I already didn't end up here. So when you said that, I was like,
You're always perspiring when you come here. You're running up here with these things. It's just hot in the bakery in general, right? How many shirts do you go through a day?
I try to go home once or twice and change my shirt every time. Yeah. When I'm doing those roll-ins, I get kind of crusty. For sure. I think I got her figured out for us moving forward. So we'll talk about it.
Oh, okay. Oh, wow. Well, this is your spot. We're going to have to put some red velvet around this. Oh, these guys already know. That's right. No, this is VIP section. Chris Mattinson out of the shadow zone. Are we good, young lady? Oh, Chris Mattinson out of the shadow zone into the sunlight. Now I made it obvious. You're on camera right now, Chris. You okay with that? Okay. Right. Logan with a mask. Thank you, Bryce. I think we should start. I think these guys are ready, so I'm going to get started.
All right.
Okay, everybody, welcome to this Talk Friday session. Thank you for being here. Hope you enjoyed the goodies. Could I hear what people had today? What did we eat? The bee sting. Could you describe a bee sting, Tim? Focaccia, marinara, ham, cheese, honey.
Ooh.
Oh, that's the bee part of it. And where were those made, do you suppose? I think I do know where they were made. Vinman's Baker, everybody. Hey, everybody. We're going to get creative every week, figuring a new way to thank Jeff for bringing all those things over for free. So thank you again, Jeff, for doing that. And we've got good momentum now. We're doing this regularly almost every Friday. So it's delightful to have you. We're going to get to the speaker momentarily, but I have an announcement. I have more than one announcement from Deanna Marshall, who's part of the physics department. So you've seen all sorts of advertisement, but I want to make sure you know about this. It's Halloween. Have you heard? I don't know. I'm going to screw this up. Hang on. October 29th is tomorrow, Saturday. Hang on now. I got two things, Chris. Saturday, October 29th, from 2 to 4, there's pumpkin decoration. Pumpkin drop. There's a pumpkin drop on Sunday, but on Saturday, tomorrow, from 2 to 4, you can come in and decorate and submit your decorated pumpkin into a contest of some sort. Please see the rest of the details here if that's unclear. But Sunday at noon, October 30th, at what time? I just said noon. There's not only a pumpkin drop, and that will be outside. Who knows about this? Outside or inside? Chris, outside?
Yes, outside on the south side of the building.
South side of the building, the physics people are going to be dropping pumpkins from the roof
Yes,
Nice.
and splattering the pumpkins onto the ground.
yes. That's not all.
That's not all. In addition to the physics folks doing their pumpkin drop and measuring velocities of drops or whatever they're doing, there's geology. Who wants Trash Cano? Who wants to talk about Trash Cano? What is Trash Cano? Who's part of the geology club that's doing this? Is it not the club? This is going nowhere. 6 volunteers?
Yep.
So that's also at the same time the pumpkin drop. So please come Sunday at noon here. There's pumpkins flying. There's trash canos exploding. I assume over here as well.
Yes.
So how would you got your choice when you show up, I guess. I don't know. So that's Sunday. Looking forward to that. Happy Halloween, everybody. Okay. We are functioning with our live stream, and we are beginning the brief introduction. I'm going into my left pants pocket. Notes recorded by Hannah Shamloo, who said, would you give the introduction? I'm like, sure, you bet. So here we go. This is Nicole Rocco, who drove up from Richland, Washington this morning, and we're so pleased to have her with us. There's a connection between Hannah and Nicole, both having connections to Adam Kent at Oregon State University. So Hannah was a postdoc in Corvallis, and Jordan was there as well, and Nicole had just taken off, also finishing up a master's with Adam Kent. So Nicole grew up in Portland. She did her undergrad at Oregon State in Corvallis. She did her master's. And I think that might be part of her talk today. Her master's project was working on the geochemistry of Tahoe volcanic zone. Possibly she was even there. Would you please help me welcome Nicole Rocco?
Hey everyone, welcome. Thank you so much for being here. I'm really excited to be here and talk to you a little bit about my crazy journey. As you can see, the title of my talk, which I'm now not seeing up there, but I'm seeing in front of me. That's okay.
Yeah.
I'm going to look here instead. Is The Life of a Dark Matter Geochemist. You probably are wondering how on earth a person with a geology background ended up in this field, and so I'm going to share that with you today. It's definitely a long and winding road. So rather than mostly geocentric presentation today, I've decided to focus a little bit more on the very windy path that brought me to my current career at Pacific Northwest National Lab. I'm going to follow that up with some of the research I conduct on a day-to-day basis at the lab, and then a bit about some of the opportunities there to share with you guys. So for me, higher education has been more than just a path to a career. It has been an experience that has encouraged me to really step out of my comfort zone and to sort of reevaluate what I wanted my life to look like. This talk is meant to encourage you to do the same, to inspire you, to instigate a little curiosity, and to share some, what I think is really interesting science that's outside of the geology box. And really to share with you too about how my background in earth science led me to where I am now at PNNL. First of all, before I move on, I'm super curious. How many undergrads do we have in here? Any undergrads?
All right.
A handful, awesome. How about master's students? Sweet, okay, great. This is directed at everybody in here, but really to you guys while you're figuring out what you want to do next in your life. Okay, so a little bit about me. Nick gave me a brief introduction here, but I did grow up in Portland, born and raised, and I went to school right after high school, like a lot of people do, went to college. I actually went to University of Oregon for a year, many, many moons ago, another lifetime ago, and I really did not know what I wanted to do. So I continued on in a career in food and wine, because that's what I was doing when I was in high school. I was waiting tables. So I went back to that career after a year at college, just to kind of regroup and figure out what I wanted to do. Well, that career ended up becoming nearly 20 years in the industry. And I enjoyed every minute of it. It was exciting and very lucrative for me, and I loved it. But when I was in my mid-30s, I grew pretty tired of customer service. I just didn't want to do it anymore. I couldn't see myself doing it forever. And I always wanted to be a scientist ever since I was a little girl. And so I figured, what, if not now, when? So I quit my job and started back to school when I was about 35. I'm an avid outdoors person. It's one of the things I love about the Pacific Northwest. I love to cycle, run, hike, backpack, and I take great pride in teaching people how to skydive. So yes, this is a picture of me here teaching somebody how to skydive. I do that on my weekends. And I'm happy to talk to anybody about that if anybody's interested later, preferably with beer and pizza. So starting over, it can be really, really intimidating, very scary, really hard. I really had to face a lot of my fears when I did it. I had to let go of everything that spelled security to me. I was a homeowner at the time, excuse me. I had a steady paycheck, health insurance. You know, I was on a good path, and I had to release all of that in order to go back to school. I didn't work during my undergrad, so lived on a very, very meager income of savings that I had, and it was challenging, but it was one of the most rewarding things I've ever done. So I started a community college, got my prereqs out of the way, and then I moved down to Oregon State in 2012, where I went into Oregon State as an atmospheric science major. I really wanted to go the path of being a forecast meteorologist, the kind that was behind the computer screen, not on TV, because everybody used to always say, oh, you want to be a weather person on TV. So when I got there, I had to start taking some earth science classes because I didn't have any that I had taken at community college. And I took Intro to Geology, and it totally changed my life. didn't even know this world existed. So by the time I was done with my first term at Oregon State, I had already changed my major to geology. I also got an opportunity through that class and through the instructor to do some undergrad research, and this sort of started the ball rolling with the direction that I ended up taking. So at the end of my undergrad experience, I did geology field camp with Logan, actually. And I ended up doing it with the University of Oregon for a variety of reasons. And that experience at field camp led to an internship with the USGS, an NAGT USGS internship. It was an incredible experience. I wasn't actually doing geology at the USGS there. It was a wetland and aquatic research center, but it gave me an opportunity to do lab work in and out of every single day. And I really, really enjoyed that. So during that internship, which was about 6 months, I started trying to figure out what I was going to do next. So I applied for a myriad of different jobs, all the way from, jobs up at the Bremerton shipyard to, jobs with the state of Oregon and private consulting firms, all different types of jobs, coupled with a couple of community colleges as well. And nothing really panned out. So when I got back from Florida, I ended up back in the customer service business, which really did not make me very happy. I did it because I needed to, and it was fine, but I had spent all this time and energy going down this path toward my dreams, and I felt like I kind of got sidetracked by having to go back to that. So while I was doing that, I came to the conclusion that it would probably be a good idea for me to go back to get my master's degree. So Adam was actually the first person I reached out to because I loved his geochemistry class so much. It was my favorite class in undergrad. And it just so happened at that time that he had just gotten a proposal funded to do a really, really large and intricate project, a big collaboration studying the volcanoes on the North Island in New Zealand. He was looking for a master's student. So we agreed right then and there that we would work together, and that brought me back to OSU in the fall of 2017. So the cool thing about this project was that it would include a lot of lab work. It was a lab heavy project, and I'd get to do a lot of different geochemical analyses. And again, this sort of started paving the path toward where I am now. Oops. Okay, so grad school. My first term of grad school included going out into the field to collect our samples. It was quite an incredible experience. I won't lie, it's one of the reasons why I agreed to do the project. Yeah, it was pretty incredible. So the group of us it was a 3-university collaboration. So big group of us got to go to New Zealand. We did about 12 days of field work. And the way that we went about our sampling strategy was we wanted to collect samples from what we're calling a full caldera cycle, and I'll talk a little bit about that on the next couple slides. So we collected samples from about 18 different units from the most recent caldera cycle. So that includes the large caldera forming eruption, and then these small but very significant eruptions that happen between the large eruptions. So we cruised around the North Island for about 12 days and brought back, oh my gosh, probably 10 giant FedEx boxes full of samples for the 3 universities. And actually, I want to point out let me use this little thing here. So I'm not sure if you can, I'm kind of in front of it right now on the screen, but there's so here's a person right here down at the bottom. This is a huge ignimbrite flow from the Matahina eruption. And here is, on this side over here, was this really great quarry that we got to sample from that had like every single layer of the Taupo eruption. So we got to see some really neat stuff. Okay, so as I mentioned, my master's project was a collaboration between 3 universities, and the point of the project was to dive into problems surrounding large silicic volcanic eruptions on a geochemical level. My portion was involving investigating mantle-derived and crustal contributions to these magmas using specifically trace element geochemistry and isotope geochemistry. So the really cool and novel thing about my project was that I was to develop methodology to measure lead isotopic compositions in situ. So we collected eruptions that had a lot of melt inclusions, And we had this new setup in our lab, a brand new multi-collector ICP-MS that we were going to partner with our laser ablation system. And we were going to try to measure very, very low levels of lead concentrations in these melt inclusions. I was really excited to help Adam develop this method. So in addition to this, I was going to complement the data with in situ trace element concentrations via laser ablation, ICP-MS, and also major elements in these melt inclusions as well. So preparing for all of this analytical work required me to assist in our class 1000 metal-free clean room, which I'd never even been in a clean room before. So this was a really cool experience for me as well. And I just got to help out with the day-to-day sort of lab chores in there. Again, another introduction of something that I now do on a daily basis. So in the first half of my second year, my project required a massive path change. We had a fire in part of our clean room that basically destroyed our entire plasma mass spectrometry lab. And the entire building actually ended up needing to be rebuilt. So it required everyone that worked in that clean room to figure out what path they were going to take next, including myself. So the instrument I was going to use, the space where we did all of our sample preparation, all that was gone. So the abrupt change meant that my project was going to shift. It meant that I was going to be doing a lot more wet chemistry. And again, a skill that would eventually lead me to where I'm at now. So the point of me telling you this is this experience really forced me to reorganize and adapt to a situation that maybe a lot of people would have just thrown in the towel and dropped what they were doing, because it was very challenging. A lot of the faculty had to focus on taking care of what needed to be done with the building, and we as students really needed to sort of be able to advocate for ourselves. So I needed to figure out where my project was going to go, how I was going to collect my data, and it forced me to really seek out other collaboration with other universities and with other geologists and scientists in general. So the focus of my project switched at this point then to collecting lead and strontium isotopes in glasses. So we abandoned the in situ portion of it because we just didn't have a method to do it. And Adam was really wanted to develop that method. So he was going to just push pause on that. So I needed to travel out of state to do that. I went to New Mexico State University and I got to work in their isotope geochemistry lab there and do all my chemistry and analytical work there. I got to use multi-collector ICP-MS, which I don't have a picture of here, on a TIMS, which is really cool. I was really excited to be able to use a TIMS to collect my strontium isotopes. And then I also did a little work at OSU as well, doing major elements on our electron microprobe. And then eventually I was able to collect trace elements through laser ablation. So after the data collection, of course, all of those techniques required me to learn how to make the corrections, do the data reduction, all of those different things I wasn't necessarily expecting to do in the beginning of my project. So again, adaptation and learning new skills, it was a really cool experience, even though it was a challenge. So every single moment of those experiences in the lab, in each of the labs, with all the instruments, all of the mentors I worked with, those led me really to feel confident in applying for and interviewing for a position that otherwise I would have never felt like I was remotely qualified for. So the point of that is just to take the time when you're, putting together your CV and thinking about what you've learned through your educational experience. You look at a job listing. What do I have that can work for this job, rather than just looking at something and thinking, oh, I'm not a chemist, or I'm not, whatever. Got to really work on honing those things in to tailor them. Okay, so I finished my master's degree in June of 2020. As we all know, that was the first summer of COVID. I think I was one of the first Zoom defenses, and it was a little intimidating, but it worked out, and I finished. But that summer was really challenging, as everybody here knows. Everybody had their own personal struggles with what was going on then, but it definitely made searching for work really challenging. A lot of people weren't hiring. It was difficult to deal with interviews. People were still getting used to the virtual platform and all that. So it was a big challenge. I had an internship at the time, or a fellowship that I was doing in Albany, right down the road from OSU, at the National Energy Technology Laboratory. but that was wrapping up and it wasn't something I wanted to continue on. So I had something to keep me busy part-time that summer, but I searched high and low for work. As I mentioned before, geography is really important to me. I really wanted to stay in the Pacific Northwest. So that also kind of narrowed down my options a bit. So I'd always been drawn to the public sector. I think I mentioned I did the USGS internship. I had already done a fellowship with the Department of Energy. So I kept feeling drawn to that path. So I knew I wanted to be a lab scientist. This is what I really fell in love with during my master's. But I was worried that I was going to have trouble finding a job in that field without a PhD. And I'm especially speaking to everyone here in probably feeling that way a little bit sometimes. If you want to go into research or go into the public sector, that can be a little intimidating, but I'm here to assure you that there is a lot of opportunity out there. But I did even consider a PhD momentarily, and I didn't follow through with it. And just to share a little bit about that summer too, I spent a lot of time exploring the Pacific Northwest, did tons of hiking and backpacking. And in the middle of doing all of these things, a girl from my cohort, my master's cohort, shared an opportunity with me for a postmaster's position at PNNL. So first off, postmasters, I had never heard of that before. I'd heard of postdoc, but I was like, postmasters, I didn't even know those types of opportunities existed. Well, they do. I'm here to tell you. And so do postbachelor's positions. So the title of the position was this. It was Postmaster's Research Associate for Ultra Low Background Materials and Assay. I was like, what? I was surprised she even sent it to me. So she had the girl that sent it to me has a bit of a chemistry background, and I didn't feel like I did. I even had to look up the word assay. I had never even heard that word in my life. So if people don't know what that is, it basically just means taking a substance or a material, breaking it down to its constituents and identifying what those constituents are. I had no idea what that meant. So that's about how much I knew about the position. But then I started looking through the description. Lab work, wet chemistry, ICP-MS. I was like, oh, I have those skills. I thought, why not? So I applied. And again, just to reiterate, tailoring that application and your interview to the skills that you have related to what the job is asking for can get you a job in a field you never thought you'd be qualified for. So by the end of September, I had accepted a limited term position. So it was a 2 to 3 year position as a postmaster's research associate. And I started to plan my move over to Tri-Cities. Okay, so what is it that I actually do at PNNL? That's the big question here. It's a rather complicated question. So I work in the physical sciences facility for the National Security Directorate in the detection physics group. So I'm on a team of chemists that works for the detection physics group. Among other things, our group's concerned with when and how the universe formed, what the building blocks of the universe are, and how we can measure them. So that's the key point right there. We create and utilize new capabilities to enhance national security. We also focus on the direct detection of dark matter, which makes up most of the universe, and the properties of neutrinos and their role in known matter. I work about half the time with the low background materials and assay team, and then I also work with a low background signatures team, which focuses more on very low level radiation detection. Okay, so why do these areas of fundamental physics research and radiation detection require chemists? I mean, again, when I read this, I thought this is a job for a physicist, not a chemist. And how on earth did an earth scientist find herself involved and invaluable in a large group of mostly physicists? I ask myself that all the time. Okay, so our team of chemists support rare event physics and low background radiation experiments. So up on the slide here, let me use my pointer. These images here, these diagrams are all pictures of, dark matter detectors. So these are built for very large scale experiments. On a couple of these pictures here, you can see, oops, I lost my cursor. Well, here you can see a person, but down over here on this one, there's a small person there. That gives you an idea about the size of these detectors. They're huge. So the physicists are searching for particles or events that might only occur or they might only see once or very few times in years-long experiments. And if they do see these or observe these events, I mean, these are like Nobel Prize winning things that happen, experiments that happen. It's pretty cool. So it's really, really important that the detector itself has a very, very low background radiation. We don't want anything involved in that detector that can interfere with this, maybe this one signal that we might see or this one particle. So the decays of these other nuclides, they can mimic or overshadow that signal. So the ways to mitigate that is to build the labs and experiments very deep underground. You can see right here, it's kind of hard to see on this picture, but this is the surface right here of Snow Lab, which is in Canada. And this is in an active nickel mine, by the way. And you have to go down 2 kilometers to get to the actual lab space where these experiments are. And all 3 of these experiments that are up here are inside Snow Lab. So building underground, and then the next way to mitigate these problems is to use what we call radio pure materials. Okay, so this is where myself and my team come in. Okay, so radioactive contaminants present in materials everywhere in life, just everywhere on the earth, these interfere with the sensitivity of the detector. So ultra pure radio pure materials are necessary for the most sensitive detection. And this is included in low level radiation detection as well. So the major players that we're worried about are these 3 long-lived isotopes that are right here: potassium-40, thorium-232, uranium-238, and their progeny. There's just a chart right here of the uranium series and the thorium series decay, and then potassium-40 down here. So they're ubiquitous in nature. They're everywhere. You can see here that they're just in the Earth's crust are at levels that are multiple orders of magnitude higher than what we need to see in the detectors. So we're talking about, I mean, potassium, 1.4%. We want the level to be, at some point, sometimes less than 1 ppm. So how do we do that? So in order to solve the problems of these intrinsic backgrounds, we need a dedicated space to analyze these materials or perform materials assay. We also do a lot of research and development in this lab and work to develop materials as well that can be used for these experiments. So we have a class 10,000 clean room in our facility, and we do all of our sample prep inside a class 10 laminar flow hood. And if you're not familiar, that just means the amount of very small particulates that are in the air. So class 10 means it's about as clean as it can be. Our instrument of choice here is a triple quadrupole inductively coupled plasma mass spectrometer. And we tune that mass spectrometer for maximum sensitivity at these higher masses for very low level measurements. So our sensitivity can get down to the parts per quadrillion on the instrument, which is like atoms basically is what we're measuring. So in speaking of atoms, the ICP-MS measures atoms, and then we convert those atoms to concentration. And then depending on what our clients need, sometimes we convert again to radioactive decays per day. So with some plots I'll show in a little bit, you'll see both of those units, and I'll point out when they change. So now that you have a little bit of background on why our work is important for these experiments and where we conduct it, I'm going to translate this to 2 projects that I work on specifically, and how we use the capability to improve these low-level measurements. So the first is about ultra-pure materials for low-level radiation detection by way of a common method called liquid scintillation counting, and I'll give you a little bit of background on that too on the next slide. Okay, so liquid scintillation counting, or LS counting, or LSC, I'll say probably one of those variants. It's a standard technique for radiation detection. It's used to detect low energy alpha and beta decays. And just in case people aren't familiar, during a radioactive decay, there's a number of particles that can be released as energy, and alpha and beta particles are 2 of those, and that's what this method is used for, to detect those. The method uses a scintillator, which I'm going to explain what that is on the next slide, to produce light from a radioactive decay. So here at PNNL, in addition, to a commercial, just off the shelf liquid scintillation detector, we have constructed an ultra low background scintillation counter, or ULB LSC, which I'll call it. Right here is a photograph of this ULB LSC right here. And then here is a diagram cross section of it. The measurement chamber is right down here. The photomultiplier tubes are up here, and that's what ends up reading the signal in the end. And then this is all copper and lead shielding around the measurement chamber. So the uniqueness of this detector, lies in the fact that it lives underground. It's about 30 meters underground. And it has a very, very low predicted background to start with. So we can measure these very low levels of radiation in this detector. Let's see here. Okay, so let's talk a little bit about the scintillator itself. Okay, in general, scintillators can be solid or liquid and made up either of organic or inorganic chemicals. So this particular study is concerned with organic liquid scintillators. They're formed by a mixture of these chemicals right here. Okay. So how exactly does a scintillator function? There's two pictures here to show this. So this little cartoon here is kind of a very nice basic image of how the scintillator functions. So put the sample in the scintillator, a radioactive decay happens and emits a beta particle. That beta particle interacts with the solvent, excuse me, and then the solvent transfers that energy to the actual scintillator or floor. That's another name for it. The floor then emits a photon of light, and you can see that here in this cartoon. I keep losing my cursor. Here we go. So once that photon of light is emitted, there's a secondary scintillator or a wavelength shifter that takes that light, shifts the wavelength to a specific wavelength that can be detected by the photomultiplier tube. That tube then converts that wavelength to an electrical signal, and then that's detected by the instrument itself. So the radioactive background, which I've been talking quite a bit about, meaning those decays that aren't associated with the sample, those can mimic or interfere that signal of interest, okay, especially in these very low background applications. So as I showed on the previous slide, the things like being the detector being built underground, these special materials that we use, those can reduce that external background. However, what if that scintillator itself is what is causing the background? So in order to attack this problem, we first wanted to measure how much background was in this finished liquid scintillation cocktail, which is what it's called. We first wanted to measure that. And then if we could, we wanted to tease out which of those chemicals, that are in the cocktail was the main problem or the main culprit there. Okay, so this plot here is showing the results from the 3 analytes of interest. So we have potassium, thorium, and uranium of a variety of finished LSC cocktails that we measure. Those are across the bottom here. We have some non-disclosure agreements with these companies, which is why it just says cocktail A or company A. And then on the y-axis here on a log scale are the decays per day per each 10 milliliter sample. So this red dashed line here is the predicted background of the ULB LSC. That predicted background is something along the lines of 13 decays per day. Okay, that's basically nothing. It's a very, very low background. So as you can see here, the orange and blue dots that are below this red line, these are thorium and uranium. No problem, they're below the background, so we don't even need to worry about those analytes. The green dots up at the top here are potassium-40. They're all above the background. So this is a problem. So once we realized that this was the problem isotope, we then needed to figure out, well, okay, what is it about the cocktail that's causing all of this potassium? Especially due to the fact that, if you remember from the earlier slide, the solvent is actually the main component. So that's an organic chemical, and we're like, where is the potassium coming from? It seems strange to us. So the solvent and the surfactant are the 2 main components of the cocktail. The surfactant makes up anywhere between 20 to 40%, the solvent about 50%. During this deep dive that we went into, we realized that surfactants are generally made with a potassium catalyst, potassium hydroxide. We didn't know that before we started this. So since we know the approximate fraction of the surfactant in the cocktail, we measured the surfactants to see if they fit the bill. Okay, so surfactant, what is that? Most people think of soap or some sort of cleaning, detergent, and that's exactly what it is. It's important for these organic cocktails because they allow aqueous samples to mix with the organic cocktail. Think oil and water. You need an emulsifier in there in order to integrate the sample into the cocktail. So the data in this table here show that the surfactants from company B have 5 times more potassium than the cocktail from company B. So if we mix, in this case, 1 part surfactant to 5 parts cocktail, which is 20%, the contamination from the surfactant alone would account for the total contamination of the cocktail. So this revealed to us that the surfactant was likely the culprit that was contributing the bulk, if not all, of the potassium to the cocktail. So this cartoon here on the right just shows a visual of that same concept there. So once we'd pinpointed the problem of potassium, the next step was to figure out how do we mitigate this. Okay, we buy these cocktails off the shelf. How do we deal with this? So we had been exploring 2 potential paths to try to figure out how to mitigate this. The first one was to utilize surfactants that were manufactured with potassium-free catalysts. And we didn't even know these existed until, again, we started doing a deep dive, and we figured that out pretty quickly, and we took these and we measured them, and sure enough, they were much, much, much lower, orders of magnitude lower in potassium. This could be really useful for a house-made or a custom cocktail, but it may be a little challenging to try to convince a big commercial company to incorporate this. So we decided that what we were going to try to do was to purify the finished cocktail at the end. So I cannot reveal any specific, that's the word I was looking for, details about the cleaning method because we're actually working on a patent for it right now, which is really cool. But we were able to lower the potassium levels by 1 to 2 orders of magnitude in the finished cocktail. There's just some numbers right here on this table showing that. Tried a couple different treatments, and one of the treatments got us all the way to a factor of 38 cleaner in that finished cocktail. And that took almost all of these cocktails that we measured in the beginning and dropped them below that predicted background. Hello. There we go. Okay, just to summarize that project, as I've said many times, and we'll say again probably, intrinsic radioactive background in liquid scintillation cocktails interferes with the sensitivity, especially on low-level applications. Through very ultrasensitive assay, we've learned that potassium creates significant radioactive backgrounds in these cocktails, and the surfactants in the cocktail are the main contributor. The 2 methods that we're currently exploring right now are potassium-free surfactants on one path and purifying the cocktail at the end of the production process. And so far, that has been showing very promising results. Okay, so I'm going to switch gears a little bit. I'm going to talk a little bit about some of the circuitry that goes into the fundamental physics detectors, but the general ideas are going to remain the same. We're going to analyze a commercial product that is innately dirty or not very radio pure, and we're going to develop a way to reduce that problematic radioactive background. Okay, so just a little bit of background on this project. So cables and circuitry, especially these flexible cables, they're used in many, many applications, from laptops, monitors, solar and wind power, all kinds of everyday applications. They're very important for rare event detectors. They're composed of 2 main components. A polyimide, which is the insulator, and that's just a type of polymer, and a conductor, which is copper. So the whole cable, even though they look complicated, are just those 2 materials. There's a large number of signal connectors or signal channels, that are needed in these very large detectors, and so it requires a lot of cabling. So that means if the cables are innately not very radio pure, and then you put tons of them in these detectors, it's going to be a major problem. Okay, so I'm going to go through very quickly just the fabrication process, because we know that we start with a very clean material. The group that I work with started researching this before I came on board, but they did a bunch of tests with a bunch of different starting materials and found a very radio pure material. And so we know that the starting material is pure. But as you can see, there's all kinds of different processes that happen while the cable's being fabricated. All the little black symbols down on the bottom show either some kind of mechanical handling, a chemical addition, or some material added and then taken away. So even though we start with those very clean materials, and now at this point we're talking around 10 parts per trillion for uranium and thorium. As a side note, this particular project isn't concerned with potassium, so it's just thorium and uranium is what we're looking at. So very clean materials. The fabrication introduces large contamination through all of these processes. So that at the end, this finished cable right here, we're looking at sometimes upwards of 10,000 parts per trillion. So way in the ppb range. So any of these steps along the way could introduce radioactive contaminants. So this project is really cool because our team has partnered with a small business, and we've received a grant to work with this small business. So we basically talk to them about what we need, and they work on creating that product for us. So Q-Flex is the name of the company. They're experts in this type of cable production. And what we did is we sat down with them and we decided that we wanted to be able to measure these cables at each step along the fabrication process to figure out where all of this contamination was coming in. And this just shows here the fabrication process. And the method that we took is we had them do the first process, take out what we call a coupon or a subsample, take that same panel, do the second process, take out a coupon. So they went down the line and did that, and then they sent all of those to us. Again, triple quadruple ICP-MS is what we use to analyze, and we can obtain that very, very low sensitivity for these samples. Okay, so let's take a peek at some of this data here. So both of these plots here show our two analytes of interest here, uranium and thorium. We've got a log scale on the bottom here, in parts per trillion. And then this red line for both of these here is showing our goal. Okay, we want to get around 25 parts per trillion. So as you can see, we start below that, and then as we go along, up it goes. So we did this systematic assay. We also assayed on the side all the chemicals they used, all the raw materials, like where is this coming from? So we discovered several steps where the contamination was being introduced. So first of all, the copper plating was the first spot. I'm just going to talk very quickly through these. The process involves several solutions, catalysts. The whole entire cable is covered with copper. And what we were thinking is happening is the contamination is getting trapped underneath that copper at that stage. So wherever we're at that stage, it seemed like we couldn't get any lower than that. So the mitigation step was to use a different type of plating that used used carbon instead, much fewer chemicals, and we were able to clean that process at the end, and it came out just as low as the starting material. The sanding was another problem. We came to find out that the company was literally using Scotch-Brite pads that were right off the shelf. There were two types. One was an aluminum oxide type, and one was a silicon carbide. So we tested those to see which one was dirtier. It was kind of silly. It's been a joke amongst us, the Scotch-Brite. So we found the cleaner one and asked them, from here forward, just use the silicon carbide. And it worked. We were able to drop that level, and it became a more consistent value as well. So steps 5 through 7, it's a process called photolithography. It's where they take the cable and basically create these traces in the cable without getting into too much detail about it. They use 3 or 4 different types of chemicals, and they send the cables out of house to do the process, so there's a little less control. So the mitigation step we were able to take is after that process, we developed a cleaning method in our lab in order to clean that cable up, and it worked really well. And then lastly, the cover lay. At the very end of the process, they put another layer of polymer over the top of the cable. Again, it traps whatever's left behind. And then that cover lay was innately not very clean either. So we did a systematic search to try to find a clean option for that. The company then included that in their process. So very quickly here, I will go over the results. So we had them create two types of cables, a very simple 2-layer cable, and then a more complicated cable. For this simple cable here, as you can see, we were able to get those levels down to almost exactly where the starting laminate was within error here. And then for this more complicated cable, not quite as clean, but we were still able to lower those values by a couple of orders of magnitude in some case, which is really cool. So just to wrap up this project and then tell you where we're going next is these radio pure cables are needed for these rare event searches. Commercial cable options are well above those backgrounds that I've been talking about, in the thousands of parts per trillion for uranium, hundreds of parts per trillion for thorium, and that limits their use in these experiments. So by working with this private vendor, we've identified key sources of the contamination, and then we have followed this unique approach of cleaning, modifying processes, and identifying very clean raw materials, and we've been able to reduce those backgrounds down to tens of parts per trillion for thorium and uranium. So currently we're working on a 2-year grant that's a follow-up of what we recently did. And we're going to continue these improvements. And then the goal is to make these clean cables commercially available and make them on a large scale. Okay, so before I switch gears to talk a little bit about PNNL, just have a couple slides for that. I just wanted to acknowledge the sponsors for both of these programs. The Department of Energy Office of Nuclear Physics Early Career Program, that's who sponsors the cables project that I just told you about, and that Small Business Innovation Grant. And then the ultra pure scintillator work for the low-level radiation detection is sponsored by the Office of Defense Nuclear Non-Proliferation Research and Development. It's a mouthful. And then these are our collaborators here. Okay, so I'm going to switch gears one more time along this windy path and just tell you guys a little bit about PNNL and the opportunities there. And then I will be done. Okay, so a little bit about the lab in Tri-Cities. I don't know how many people here or that are listening in have been to Tri-Cities. So the lab is located in North Richland in Washington. We're now up to almost 6,000 employees at the lab, which is crazy. It's a huge, huge campus. We're the largest non-agricultural employer in the Tri-Cities. So the town, Richland, definitely has like kind of a lab vibe to it. I love it. The Tri-Cities itself, it's a shrub steppe ecosystem, dry grasslands, lots of sagebrush. I love it. I grew up in Western Oregon, and so it's totally the opposite of what I grew up in. So I think it's such a cool place. The geology out there is so awesome as well. We only get about 8 inches of rain per year, which I also love, being from Portland. We have 4 really distinctive seasons, which I love. Hot summers, cool to cold winters, a little bit of snow, and gorgeous and temperate falls and springs. Our shoulder seasons are incredible. We're also at the confluence of 3 rivers. So along with that shrub steppe ecosystem, we have an incredible riparian area in Tri-Cities. When I first got to town, I was like, it's so green here. I was shocked. But yeah, lots of fir trees, deciduous trees. It's really beautiful. Lots of water activities, cool local desert hikes. I spend the whole winter hiking in Eastern Washington. And the town is pretty bike friendly as well. Richland obviously has a very, very rich and interesting history. Most of the town was built in the 40s during the Manhattan Project, when the government shipped a bunch of people over to work on that. And then the lab was established in the mid-60s when they split up the R&D part of Hanford. So that's how long the lab has been there. So I think I mentioned this before, but there's copious opportunities at the lab. And my work is centered around fundamental physics, but there's tons of geologists that work in the physical sciences facility, lots of environmental scientists, and tons of opportunities. So I plan on sending out an email either to Hannah or Nick or both with a bunch of links, but I just wanted to put this up here. We have a lot of STEM internships. We have tons of post-bachelor's and post-master's positions. We have about an 80% retention rate for postgraduate positions. So if you're interested in working at the lab and you come in as a post-batch or a post-master's, there's a good chance that you will get hired on to stay permanently if that's what you desire. So I highly recommend checking out these websites. As you can see here, we've got opportunities in a wide variety of fields. So yeah, I encourage you to check it out. And with that, I'll take any questions.
Yay. Thank you, Nicole.
Yeah.
Questions for Nicole, and she's going to repeat your question for the home audience as
Just a
well.
reminder.
We're ready for you. Here we
Oh,
go.
come on, guys.
Questions?
Yeah, please. Oh, she asked if I was on LinkedIn. Yes, but I have not been very active with it. So, but yes, I am on there, and I'm pretty sure it's up to date with my current information.
We've been trying to promote a lot of the interns. Our group is following PNNL.
Awesome.
So if you are there or share things.
Yes.
They'll get.
Perfect. I will. Yes, I am on there. I need to log in and make sure I have. Yeah.
Maybe a roundabout question. When you had your, when you were in your master's,
Yeah.
you were learning about, the different instrumentations that you had to do. What was really helpful for you when you were approaching, a complicated instrument and like how to get the best, data out of it and also your best interpretations out of it?
Yeah. That is a great question. So the question was, how did I work to get the best data and the best interpretations out of each of the instruments that I used? That it's really hard to do that, especially in a master's program, I think, because everything happens so fast. It's really a sprint. It really is. But I took the time to do a little bit of reading ahead of time. I know this sounds silly, but even just reading an instrument manual can be so helpful because it'll give you even just bits and pieces of how to optimize that instrument. I took the time always to take copious amounts of notes. I'm one of those people that has to make people stop constantly because I'm writing everything down. Took lots of notes when I was being taught how to use the instrument. And then I have had more of a chance to do this now that I'm at the lab because I have basically carte blanche use of our instruments. I didn't have that when I was in my master's program. I would just sit down at the instrument, light it up, and start messing around with stuff. That was really how I got the best experience. But I just took a lot of notes, absorbed everything that I could, and some stuff sinks in, some stuff filters out. As far as interpretations go, this may sound like a sort of canned answer, but diving into the literature on whatever you're working with is a really great way to do it. Your data doesn't always match up with what you see in the literature. And I didn't go into detail about that with my master's, but I definitely ran into that. My data did not match up with what was in the literature. So that started forcing me to ask why. And then I started going down different rabbit holes to figure out why. And ultimately, I didn't have enough time to really suss that out. But taking opportunities to look at references and take a left turn or right turn when you need to can really be helpful and useful. I hope that answered your question. Yeah. No, please.
You mentioned that as an earth scientist, you bring something to your group that others don't have.
Yes.
What do you feel like you bring as a geoscientist or earth scientist to that?
Yeah. Yes. Yeah, that's actually a really great question too, because I asked that when I first started, why they hired so many geologists. The question was, what do I bring as an earth scientist to my group of chemists and physicists? And in all honesty, I did ask that because I was part of a group hire, and we were all 3 geologists. And I was like, why are you guys hiring geologists? I'm so confused. And my boss at the time said to me that they really appreciate the multifaceted way that earth scientists approach problems. And I was I had to agree with him. I was like, you're right. We think about these really complicated problems in a variety of ways. We deal with chemistry. We deal with all different types of sciences within the earth science. And I think we have a really nice, broad base for our knowledge set. And because I look at the people that I work with, and their knowledge set is very, very pinpointed and specific, which is great. That's what's needed for that type of work. But I think that having a broad base of viewing things a little more zoomed out has really helped me a lot. I work with a lot of people that have bachelor's, master's, and PhDs in chemistry, and they view problems differently than I do. So I think it adds a lot to our group. Yeah.
Thurston Miller is at home. He wonders, is post-bachelor's something that is common at various national laboratories?
That's a really good question too. So I'm not exactly sure of all of the opportunities that are at other national labs, because our lab works kind of in a specific way. Even though we're all under the Department of Energy umbrella, there's like different methods to how people, or how the different labs hire.
We lost your mic.
Oh, did I?
You're fine. You're fine.
Oh,
You're just
okay. I don't know where to start over.
I'm sorry.
No, that's okay. Basically, the short answer is I'm not 100% sure if other national labs offer that. I have seen those opportunities at Los Alamos, but I haven't looked that deeply into other national labs. I would imagine that there probably are. It depends on what is being conducted, what type of research is being conducted at those labs too, because certain labs have higher security levels than we do for certain things. But it doesn't hurt to look. I mean, just a simple Google search of post-bachelors for, DOE national labs will probably come up with a lot. But I do know we have tons of opportunity at PNNL. So
That was an excellent talk. We're down to one mic, so let's thank Nicole for that talk, please. Faculty, staff, anybody really, if you want to come up and visit, that's great. If you want to continue and go to Kikuchan and have some Japanese food with us, by all means. If you want Nicole to come and visit you in your office a little bit later on this afternoon, please. We'd love to. She's here for another few hours, so don't be shy. Even Cornerstone Pizza, I think, at 4 o'clock. Come on down. Okay? So thanks for coming, everybody. Thanks again, Nicole. All right. That was outstanding. You did a great job.
Thanks.
Oh my God. Yeah. So I'll let these guys come up. Yeah, your turn,
this off
just in
because-
case. Yeah.
okay.
I'm going to talk to this home crowd, but I'll let them kind of handle you. Thank you. Well, maybe you can still hear me at home. And if that's true, actually, can I ask, are we 5 by 5? Can you hear me? 5 by 5? Can you hear me? Okay, thank you. Let me get the right camera here. That's the wrong camera. Let me get the right camera. All right, I got to think for a second. Here we go. Let's do that. So, just in case my mic is about to go out, let me, I can't answer any questions. Come on now. I tried. I really tried to comprehend that. I thought it was an excellent talk. That's me personally. But chemistry is a weakness of mine. So you were probably further along than I was with that. Let me say a couple quick words to finish up, and then we will see you next time. Programming note, these Friday at noon talks continue, and I will be posting an announcement like the day before, I don't have the schedule handy right now. I didn't even think to grab that, but I know what's next Friday? November 4th, maybe? Whatever. The first Friday in November, we will have Will Hoover from the University of Washington. That will be another earthquake talk. Off the top of my head, it's episodic tremor and slip in chemically something about details from a subduction zone and tying it to something called ETS, episodic tremor and slip. I promise I'll have the talk title figured out soon enough. I hope it's clear to you by now, we have a variety of talks planned. Geology is broad, and yes, it goes into chemistry, and yes, it goes into physics, and yes, it goes into the ice age and landforms and everything in between. So we'll have a whole variety of, it'll be a variety platter for you, essentially, if you keep with us with these Talk Friday episodes. I know most of you are watching this in replay, so thank you for finding the replay, and I hope that you enjoyed it. And for those of you that are live, let me interact with you for 3 more minutes, and then I'm shutting this off. Weirdly, the brain computer, even though it's plugged in, has lost power, so I don't know what that's about. Anything you wanted to say? Let me ask before we quit, where are you viewing from, especially if you joined us late? Just curious. How many do we have? 330 folks. Right before I sign off, where are you viewing from, and will I be seeing you when we start the Baja BC series, A to Z, in a few weeks? The Netherlands, Garrett, the Dutch Night Owl. Hello, Notre Dame, Indiana, Los Angeles, California, Everett, Washington, Media, Pennsylvania, Bethesda, Maryland, San Diego, California, Selah, Washington, Warwickshire, UK, Northern Utah. DHGO is from Saudi. Hello to you, live. That's fun. Apex, North Carolina. That's also fun. Please don't be hurt. Dorset, UK, Albany, Georgia. Thank you, Rapid Rick. You like the format that we're doing here. It's new. I'm still working it out. I'm super stressed every Friday morning. I teach at 10. I have all this stuff set up, and my 101 students are like, peering around all this stuff to listen to the lecture. And then we got to set up the Vindman's thing and everything else. Martin from Slovakia. Hello, in Europe, New Jersey. I'm down to live here. Yeah, and if you haven't, leaving a few nice comments about our speaker today would be much appreciated, I'm sure, by her and others as well. It's always tough to give a guest lecture. This is a whole new thing where you know that you're agreeing to give a talk here, but you know that 20,000 people are going to watch it in replay. So great job to Nicole. We're meeting most of these folks for the first time. So it's a weird thing where you have someone walk in the building. They've never been here before. They only know like 1.5 people, and we make it all happen. So it's a whirlwind for these guests. And so knowing that these comments are positive will help. Well, let me just say it. This last thing I'll say. This is a new format. When Hannah and I invite speakers, I give them the link to watch the replay of these shows so that they know what they're in for. And you're really good with your comments. I'm sure today's no different. But I think if there's a bunch of neutral to / negative comments in the live chat about the speaker, we're not going to be able to get some people to come and give these talks in this format. They're not going to want to face all that. So one way you can help what's going on here is share your genuine positive comments about talks that you enjoy here in this Talk Friday series. I'm not forcing you to do that, but there's a benefit, an extra benefit for you being positive in the live chat. Okay, that's enough. We got a nice group. I'm going to swing you back around. Before I say goodbye. I assume you can still hear me. Oh, we've got Bryce Licker, Bryce the Rock Licker, Chris Mattinson, etc. So, thank you everybody for joining us. I love you, and we'll see you next Friday. Goodbye from Ellensburg, Washington, USA. You signed your form, didn't you, Hannah? Come on, you signed your form.